guys! So today we're switching it up a little bit and I'm going to talk about chemistry for the first time on this channel. Okay, so right now we are doing empirical formulas. So that's what EF stands for. Empirical formulas and molecular formulas explained. So the first way you can discover empirical formulas is through combustion analysis. So what is combustion? It's when you have a substance in this little petri dish. It's red, and you add some oxygen to it, and it gives you water and carbon dioxide. So basically, when you analyze the quantities of this carbon dioxide and the water in comparison to the sample, you'll be able to establish either one of those three very easily through grams, molecules, moles, whatever you can imagine. Okay, and there's a process that you must know when you go through this process, which is you go from percentage, if it starts, whatever you start with, percentage, if you start with mass. So for percentage, you go to mass, you'll need to go to moles, you'll need to go to the dividing. So I'm going to talk about that a little bit more. Empirical formula, and then you'll reach the molecular formula. So if you have the percentage of water and carbon dioxide, you'll need to convert it to mass, moles, divide. Empirical formula, molecular formula, and all that jazz. Okay, so I'm gonna put this in a little square because this is the square that you'll need to know when you solve for empirical formulas. Okay, so this is given in percentage, obviously. Mass is given in grams. Moles are self-explanatory. They're given in not moles, they're given in moles. And here you'll have to divide by the least. So divide by the smallest number, which will be explained when we get there. Empirical formula. And the molecular formula, which is usually the goal of doing this whole entire process. So you can screenshot this page because this is what you'll need to know. Okay. Oh, this arrow is backwards, actually. I did not notice that. Okay. Now, we're going to look at this example. Erythrose is an important chemical compound in chemical synthesis. It contains carbon, hydrogen, and oxygen. So that means our sample is made out of C's, H's, and O's. So this O is going to be a little curly, so you don't mistake it for a 0. Okay. Combustion analysis of a 0.700 gram sample yielded. So we're going to start, our sample is 0.700 grams of this CHO substance. It yielded 1.027 grams of carbon dioxide and 0.4194 grams of water. Okay. So we're going to have our CO2. We're going to have 1.027 grams of it. And we're going to have our water here, which we have 0.4194 grams of. Okay, this part we'll leave to a little bit later because it does not concern us right now. Okay, so what they're telling us to do here is determine the formula, the empirical formula of erythrose. So first, we're going to need to find... So, wait, let me ask you a question. What do we have given here from the percentage, mass, moles, divide, EF, MF? So where are we starting right now? We're starting with the mass. Why? Because we're given everything in grams. So that means our next step is to go to moles. So we have to find the number of C, H, and O's because we have carbon dioxide and water. So to find the number of C's, which I'm going to do in blue, so here is finding C, we're going to start with our given, which is 1.027 grams of CO2. Now we're going to start using a few conversion factors to find how much carbon we have in grams. So to do this, we're going to need our number of grams per mole, which is this much grams of CO2. You know why? Because we have 12.01 grams of carbon, and we have 2 oxygens, which is 32, which will give us 44.01 grams of carbon dioxide. This is important to know because when we do our conversion factors, you're going to need to know this. And this is in 1 mole of CO2. Now, in 1 mole of CO2, we have 1 mole of carbon, right? Because our goal is to get to grams of carbon. So we're going to keep conversioning until we get our carbon. And so in 1 mole, we have 12.01 grams of carbon. That's it. We got the grams. See if they all cancel out correctly. Grams of carbon dioxide, moles of carbon dioxide, moles of carbon. We are left with grams of carbon. Fantastic. Okay, now we're going to need to do some calculations over here. So we're going to start with 1.027. And we're going to multiply that by 12.01. And we're going to get this, which we're then going to divide by the 44.01. Right, that's correct. And we're going to get our result, which is 0.2803, because we're going to round to the fourth, significant figure. All right. So now that we've got our carbon down, we're going to move to our hydrogen, which I'm going to do in yellow. So to find our hydrogen, we're going to do the same thing. We're going to do it for hydrogen. We're trying to find the mass of H. So we have 18.02 grams of H2O. You can do the calculations to get the same thing. 1 mole of H2O. And in 1 mole of H2O, how many H's do we have? We have 2 moles of H, right? H2. So we have 2 moles of H. Now, in 1 mole of H, right? Because you need the grams, not the moles. 1 mole, that's a very bad mole. That in 1 mole of hydrogen, we have 1.01 grams of hydrogen. Now we're going to go back to our calculations. 0.4194 times, times 2. Now we're going to multiply that by 1.01. Now we're going to divide that by 18.02. We're going to get 0.04701. We're not going to round up. So we only have 4 sig figs. 4 sig figs. All right. So now we have our grams of carbon, and here we have our grams of hydrogen. So now that we have our grams of hydrogen and our grams of carbon, we're going to subtract them from the total sample so we can find oxygen, right? We did our carbon, we did our hydrogen, now we just need to find our oxygen. So our sample is 0.700 grams, and we're going to try to subtract the sum of the hydrogen and the carbon. 0.2803 plus 0.0470, and we're going to get our number of O's, your grams of O's. So 0.700, we should do the sum first. 0.2803 plus 0.0470. Okay, now we're going to do 0.700 minus our last answer. I get 0.3727. Okay, that looks pretty correct. So 7.27 grams of oxygen. See, 2 zeros so we don't get confused. Okay, awesome. So now that we have all of those, I'm going to write them down over here so we just have a clear understanding. 0.2803 grams of hydrogen. Oh no, that's carbon. Oh no. Carbon, grams. Okay, hydrogen. Okay, and we have oxygen now. Okay, amazing. So now what we're going to do is we need to go from mass to moles. So to do that, we simply need to divide by the molar mass. So for carbon, we're going to do this divided by 12.01 grams, because that's how much carbon weighs. So 0.2803 divided by 12.01. 0.0233. Okay, 33, that's it. Moles. Whoa. Okay, here we have 0.047D divided by 1.01. 0.047D divided by 1.01. We're going to get 0.0465 moles of hydrogen. And last but definitely not least, we have our oxygen, 0.03. Whoa, not 0.03, 0.3. Don't make mistakes, guys. Do not. Divided by oxygen is 16 grams. 16. Whoa. 0.0233. All right, moles of oxygen. Now we've completed this step. Now we have our divide by the least step. So which one of these has the smallest number of moles, the least number of moles? It's these two are the same actually. So it seems like they have a 1-to-1 ratio. This is probably going to be 1. It's going to be 1 as well, because they have the same number of moles. So now we're going to do 0.04. Oh no. Yeah. 465 divided by 0.0233. And this is basically 1.99, which we're going to take as a 2. All right. So there we have it. There's our ratio. C1H2O1. That is our empirical formula right there. Empirical formula has been determined. Okay, but we're not done yet, guys. Don't be too happy yet. Okay, so the next part is to determine the molecular formula of erythrose. So it says a 250-gram sample of erythrose contains 1.25 times 10 to the 24 molecules. Okay, gotta write that down. So a 250-gram sample of erythrose contains 1.25 times 10 to the power 24 molecules. So how much? Let's try to find the molecular formula from this. So if we have 250 grams, let me introduce you to this formula, which is the molecular formula over the empirical formula gives you the ratio. So you know how much to do everything by, how to multiply, to remove, shit. Like what should we do? Okay, so we have 250 grams, and we want to find grams per mole actually. So we're not done here yet, right? We need to make this into moles. So we have 1.25 times 10 to the power 24 molecules. So in 1 mole, we have 6.02 times 10 to the power 23 molecules. And we have 1 mole of erythrose. Okay. Gotta grab our calculator again. 1.25 divided by 6.02. And then we'll still have 10 left over, so times 10. We'll have 2.0764. Oh, 076 moles. So we need moles to grams. So we'll have grams per mole. So in 250 grams, we have 2.076 moles. So really, in 120 grams per mole, we have 12.01, 1.01 times 2, and 16. So let's do that right over here. Plus 16 plus 2.02 is 30, 10, and 30. 30.03 grams per mole. So we'll do 120 divided by 30.03. We're going to get 4. So that means our ratio is 4. So let's ratio out this little formula right here. Let's bring it down. So that means for every 1 molecule of CH2O, which is our empirical formula, which you can see back over here, we have 4 of 120 of the actual molecular formula. So that means to go from empirical to molecular, we must multiply by a ratio of 4. So this C times 4 is C4, H2 times 4 is H8, and O times 4 is O4. And there you have it. There is our molecular formula of erythrose. Thank you so much for watching. I hope you understood. And if you don't, leave a comment and I'll answer it. And yeah, thank you. Bye.